You open the AWS console. You create a folder in your brand new S3 bucket, drop a crucial image file inside, and then your application code tries to traverse the directory tree to find it. And then the code crashes. It completely breaks down.
So why did that happen? Well, it's because you treated S3 like a standard hard drive. And in doing so, you fell for the single greatest illusion in all of AWS. The truth is, S3 folders are totally fake. They just do not exist. Let's dive right into how S3 actually works under the hood so you never make this mistake again.
Let's get this straight right off the bat. Amazon S3 is not a file system. You can't install an operating system on it, and you definitely can't mount it like a traditional drive. It's an object store. In a normal file system, data lives in a strict physical hierarchy. You've got main directories nested inside other directories, kind of like a giant filing cabinet. But in S3, it's a completely flat namespace architecture. You essentially just have two things. You have a bucket, which is simply a region-specific container, and you have objects, which are just your raw files and their associated metadata, all living side by side.
Now, you might be wondering, how did you just create a folder in the AWS console? The reality is, you didn't. What you actually created was an object with a very specific key. The key is simply the unique flat name of the object. If you name an object images/profile/user.jpg, the AWS console sees those forward slashes and pretends it's a folder structure, really just to make your human brain happy. But to S3's backend, that entire string is just one single flat identifier.
Because S3 is a flat object store, it relies entirely on the web. It's completely API-driven. Every single time your application uploads, downloads, or deletes a file, it's making synchronous REST API calls over HTTP. Specifically, you're making put, get, and delete operations. Think about that for a second. Your code isn't moving files around on a local physical disk. It is interacting with a highly distributed, massive web service. Because of this fundamental difference, Amazon S3 automatically scales to handle absurdly high request rates. It distributes your objects redundantly across multiple availability zones to guarantee what AWS calls 11 nines of durability. That is 99.9999999%. To put that into perspective, if you stored 10 million objects in S3, you can expect to lose a single file once every 10,000 years. S3 also provides strong read-after-write consistency. That means the absolute millisecond you receive an HTTP 200 success response from a put request, that new object is immediately available to read worldwide.
But here is where everyday developers fail in production. Imagine you let your users upload massive 5 GB video files using a standard, basic put request. The upload crawls along, taking 20 long minutes. Then, the user's cell network blips at minute 19. The request fails, and you have to start all over from byte 0. It is a horrible user experience and, honestly, a massive waste of time and money. To implement this correctly as an AWS developer, you absolutely must use Multipart Uploads. For literally any file over 100 megabytes, you use the AWS SDK to break the file into tiny chunks and upload them in parallel. If one single chunk fails because of a network drop, you don't start over. You just retry that one tiny piece. It's infinitely faster, highly optimized, and far more resilient.
Now imagine this really common scenario. A user uploads a profile picture and you instantly need to resize it to a thumbnail. If you process that image synchronously on your backend web server while the user waits, a sudden viral spike in uploads is going to completely choke your compute resources and bring your app down. Instead, the AWS way is to build an event-driven architecture using S3 event notifications. Here's how that flows. When a new object lands in the bucket, S3 instantly detects the put operation. It immediately fires an event directly to an AWS Lambda function, an SQS or an SNS topic. Your Lambda function then wakes up asynchronously, resizes the image in the background, and saves the thumbnail back to S3. And the best part? Your main server never even knew it happened. It just kept running perfectly smoothly.
Now, let's pivot just a bit. You really need to watch out for the security and access traps here, especially if you're studying for the DVA-C02 exam. This right here, this is exactly where people mess up and accidentally leave data exposed.
For example, how do you grant a mobile app user temporary access to upload a file to a deeply private bucket without hard-coding your permanent AWS credentials directly into your app? You use a presigned URL. Your secure backend generates a cryptographic, time-limited link and hands it to the client. The client then uses that exact URL to upload the file directly to S3. No credentials shared, fully secure. It's a real game changer. What about protecting your data from yourself? If you accidentally overwrite or delete a critical file, S3 offers a feature called versioning. But here's the trick you need to remember. When versioning is enabled and you hit delete on an object, S3 doesn't actually destroy the data. It simply places a delete marker on top of it, making it invisible to standard GET requests. The old version is still sitting right there, and you are still paying for it every single month.
To stop your AWS bill from exploding due to all those hidden versions, you have to configure a lifecycle policy. You set an automated rule that essentially says, Day 0, stored in S3 standard. After 30 days, automatically move those old versions to S3 standard infrequent access to save a big chunk of money. Then, after 90 days, transition them entirely to S3 Glacier, where storage costs just pennies, but retrieval takes a few hours.
Or, if you have absolutely no idea what your access patterns look like, maybe a file is hot one week and totally ignored the next, you can just use S3 Intelligent Tiering. This storage class automatically monitors and moves objects between tiers for you based on exactly how often they're actually accessed, optimizing your costs without you having to lift a single finger.
Finally, you need to remember the critical difference between IAM policies and bucket policies. IAM policies dictate what a specific user or role can do across AWS. Bucket policies, on the other hand, attach directly to the S3 bucket resource itself. This fundamental difference makes the bucket policy the absolute perfect place to enforce strict global rules. Things like completely blocking unencrypted uploads or enforcing the public access block to ensure absolutely nobody can accidentally expose your private data to the public internet.
Okay, let's lock this down. Here are 3 rapid takeaways from this explainer.
Takeaway number 1. S3 is a flat object store, not a traditional file system. Folders do not exist. They are just an illusion created by forward slashes in your object key.
Takeaway number 2. You must optimize your performance and reliability by using Multipart Uploads for large files and secure your access by using Presigned URLs to give clients direct, temporary access to your buckets. Takeaway number 3. You control your growing costs by using lifecycle policies to transition data to cheaper storage classes like Glacier. And you protect that data by combining S3 versioning with a solid understanding of delete markers.
And one final warning before we go. S3 has an amazing feature for static website hosting, but it only hosts static files like HTML, CSS, and client-side JavaScript. If you try to upload server-side code like PHP or Node.js, S3 will not execute it. It's just going to let the user download your raw source code, exposing your entire backend logic to the world. So the next time you're building in the cloud, ask yourself, are you still treating AWS like a dusty old hard drive, or are you ready to actually harness the power of a highly distributed object store?